Vagif Abilov is a Russian-Norwegian developer working for a Norwegian company, Miles. He has about 3 decades of programming experience, currently focusing on building systems in F# and C#. Vagif is a frequent speaker at software conferences and contributor to some open source projects. In his free time, he talks to house pets and struggles with playing music. And some of you might remember him from 2016 when he was here. He was talking about the actor model. So is there anyone who remembers Vagif? Can you raise your hand? Yeah, there are a few guys. Okay, so Vagif said this is going to be a kind of a retrospective on that and some updates. So you want to be an actor. Lessons from implementing the actor model, and let's welcome Vagif Abilov. So Vagif, the floor is yours. A round of applause for Vagif. And let's just head to Pine to get ready to write the questions.
Thank you very much. Thank you for introduction. Yes, it was me who did the talk about akka and actor model 5 years ago at Build Stuff. And actually, this is a picture from Build Stuff 2015, but that was not year where I was talking about Acta. It was a year later where we already put our system into production. I was talking about why we switched to actor model and akka, and and what we achieved there. So you can ask maybe the question right at the beginning. Okay, so you're going to do some retrospective. Does it mean that the talk was wrong, or there were some false statements in this talk? Well, generally, no. It was the introduction into an actor model and why we decided it was all right. But, of course, working for several years with some technology, you find some areas which you wish you had maybe greater focus in the beginning. You find things which are maybe harder to achieve, and also you need often to change your mindset. So I think when we started with the actor model 6 years ago, we were very much some OP driven in terms of classic OP, because my GitHub nickname is Object, and my Twitter handle is OOObject. So, I have I've been using some time with ObjectOriented development. So, of course, it had affected my mindset. And in the beginning, I think I was applying it to the actor model in a way that I wouldn't do today. So partly this is talk about like a change of mindset, like change in this approach to design. So a couple of words about our product. I won't spend very much time on sort of domain related thing, but this is a media publishing company. It's Norwegian Broadcasting Corporation, NRK. It's analog to British BBC. So you can understand that things which we do quite critical, because it's 24/7. It's radio programs, TV programs, it's news clips, and it needs to be scalable, robust, available. So we had to choose technologies that really proves to be to answer all these questions and requirements. And this slide, actually, I've taken from 5 years old presentation, which it's a system sort of at large, and it hasn't changed much. It's still valid. We have media distribution engine, which gets some cute commands, and it enriches them with some metadata, and it then gets files from media archives and uploads them to CDN, Content Delivery Network. And then if you go one step deeper, we will find that, okay, it's running in a cluster, and there's command adapter and command dispatch. It uses event journal, all actor model implementations, they typically use event journals, akka does, and there is a transport layer which talks to CDNs. So this is also a relatively old slide. So first, to summarize, why actor model? Why did we choose that? When I was reading about the actor model originally, I read that it was good for proper modeling of real-world processes and interactions, and that it models some physical processes well. And for me, I read it more like a sales pitch, because if you any paradigm, any software paradigm models, we have to model real world. OP models real world. And of course, they will tell you that OP evangelists, okay, that's a great reflection of real world. You have sort of mammals, you have dogs, you have instances of dogs which you can give names, you can call method bark and the dog will bark. And so in the beginning, I didn't really appreciate this sentence, but we will go through that. Why I believe now that actually the actor model models the world better, especially when it comes to interactions. And because of proper modeling of the real world, it can have very simple threading model. So you don't need to spend much time on multi-threading issues. You won't find in our source code words like thread or lock. We don't do that anymore. And before that, it was a big hassle. Actors are very fine state machines. It's typically the single responsibility unit of your system. It's easy to test, so it's another advantage. And they're cheap to create, and they have huge scalability. And also they can be resilient, so they can take care of themselves. And you can use so-called supervision strategy. So actors have supervisors that can take care of the failures. So you can get rid of a lot of like try-catch, ugly blocks than you typically have in your C++, Java, and C# programs. And we're also using Akka cluster. It's an actor model in a cluster, and reasons are quite obvious. It scales out. We can reach high availability. You can also practice stage rollout, because you can release some features just on some nodes to try it out, something which large companies like Google and Amazon does. We don't do it in practice, but it's there. And actors have referential transparency. So that means that an actor, you program an actor the way you program with or without cluster. You don't need to think that actor can be running in a cluster. That's also a great advantage from programmers' point of view. So first and probably the most important lesson, and that was a lesson which took longest time to grasp because it required change of mindset. Don't use OP to model interactions, and by OP I mean classical OP as implemented in languages, mainstream languages like C++ and its derivation like C# and Java. And ironically, Alan Kay, who is inventor of the term object-oriented, specifically mentioned, he had to mention that he never had C++ in mind. So what turned to become OP definition, it was not as Alan Kay meant it to be. So what did he mean? He meant that objects that are like biological cells. You see, we come to similarity with real world. And they only are able to communicate with messages. This is exactly what actors are. They're only able to communicate through messages. And OP for Alan Kay means only messaging, and also protection and hiding of state process. So you can't really get state of an actor by using some property. Actors don't have properties. They only accept messages. You can request state, and that may come as a different message if actor chooses to respond. So this is all. So this is actually Alan Kay pretty much thought about actors when he was talking about object-oriented in his original definition. So why I believe now that classic OP doesn't really correspond to real world. When I was learning C++, that was my first object-oriented language I learned. And probably like some other students in university, I was fascinated with how beautifully it reflects the world. Okay, we have mammals and we have class dog, which inherits from mammal, and you can define a name of a dog, and there is a method bark, and that's so beautiful. So you can create an instance of a dog and just call .bark, specify what to bark, and dog will bark. And now, after working with the actor model for several years, I'm really amazed, puzzled. Why didn't I see something wrong at that time with this approach? Because you can easily see what can be wrong if you look at this implementation through threading perspective. Let's say you have a couple of threads, and then in first thread you created a dog, and there is another thread which can get hold of the same instance, like get some dog, and then at the same time the dog may be requested to bark in 2 different languages. And if this is not something which dog is capable of, it may explode. So this dog is not thread safe. It can't handle 2 simultaneous requests to mutually contradictory requests at the same time. So, and why is that? Because there is no life actually in dog itself. When we define dog in traditional object-oriented way, it's those who control threads controls the dog, and the dog lives in a thread. It may actually live in multiple threads if multiple threads have get hold of the same instance. So this is how it actually looks. So we don't really model dogs with classical OP. We model some pictures of a dog, some models of the dog that can't do anything, and then so we need somebody who controls them and tells them all the time what to do. This is not how real world functions. We're not standing and waiting for anyone telling us what to do. We actually make some decision, and I have a dog. And then it doesn't matter if I tell him to bark or not to bark. He makes his own conclusion. And he'd rather bark than not to bark, but anyway, it doesn't depend on my will. So how did it really affect us in our system design? What we saw that in the first years when we started implementing our system, we had still a lot of managers and dispatchers, because for us it was not natural that like small entities like files, for example, they can take care of themselves, because file is like a dog. No, it has no right to control its own life. There must be file managers, there must be file dispatcher, and soon actually we hit various types of complexities and even problems because of that, and then we realized that that's not really a way how you approach things when using the actor model. Even we were using actor.net. So actually every resource is a candidate for being an actor. So actors are very cheap. Like an empty actor which you create in C# or Java, it takes just a few hundred of bytes. And it's a reactive piece of software, so if it doesn't get a message, it doesn't consume any CPU. So you can create actors for anything, like user accounts, shopping carts, files. So anything that that can be interesting to communicate with or alter its state can be an actor. So just to give you an example of change that we later made. So this is different comparing to our first version of the system. We had a file dispatcher. So in the first implementation, okay, we have a lot of files and we need to upload them to the cloud. So we have some file processors. And then, of course, we need file dispatchers that are responsible for that. So it takes files and then it sends them file processor. But it's important that the same file gets commands through the same file processor. So it's file processor shouldn't compete for the same file. So we use so-called consistent hashing routing. So we took a hash of the file, and then so there is a guarantee that the same file only goes to the same processor. And Akka gives several routing strategies, and we used what was called consistent hashing. So it was not particularly wrong, but it was actually overcomplicated, and especially when we went to the cluster path, we realized that we can write more simple code and achieve things in a more straightforward way if we designate being an actor to the actual entities we're working with. So we got rid of file dispatchers. So every file is an actor. And we don't need any consistent hashing strategy here, because if every file is an actor, then of course it will be guaranteed, because actors get messages sequentially. That's guaranteed by the actor model. So it's solved for us. so all messages will come sequentially for this file 1 and then for file 2. So and then of course it chooses which file processor it gets, and then the rest gets processed in the same thread by not necessarily the same thread, but by the same file processor. So this is how architecture became less complicated, because we started treating entities, small entities, as individual actors. Lesson 2. Keeping actor persistence at aggregate root level. This is this was another important lesson, probably the second most important lesson. When we started working with Akka, we decided that we put persistence on various levels, and you have many levels when you dealing with file transfer. So we have Mediaset controller, which gets some commands. Okay, let's persist them. And then we have files. We also have persistence on files levels. We have transfer workers. We want to persist last state of transfer worker. So it was something like this. So you have various levels of events which are persistent. What quickly became problematic is that we often need to look at the state of the media set, which is a set of files. What is the current state? But the current state is spread among sometimes 20, 30 different actors, and they're all running in a cluster. So in order to collect current state of our media set, we have to start asking a lot of small actors, what is your state? What is your state? And then we summarize the state, and which give us total media set state. That's very, very inefficient. And the problem with this approach is that we didn't accumulate the state on aggregate root level, because if we had the state there, we could just ask the media set actor, okay, what is your state? So second generation persistence looks like this. So all our events, all what is interesting from persistence point of view, what we need to persist, we just put on the aggregate root level, and they are stored. Which means that we can't really persist file 1 state, file 2 state. We send events back to Mediaset controller, and so we have here eventual consistency situation. So maybe file 1 is already completed, but Mediaset controller hasn't been informed about it yet, because event is on its way. So in your system, you have to be careful about things like that, because maybe in some systems this is not something you can accept. Maybe you want current state to be persisted at every level because your system is not idempotent. In our situation, it was easier. The worst which can happen, the file will be uploaded twice. So what? It happens once in a while, no problem. Sometimes it's not acceptable, but if you can go to this eventual consistency approach, it will save you a lot of networks calls, a lot of event journal records. So it really gives you much more simple system. That leads us to lesson number 3. Don't expose actor state directly from the persistence layer. I was, in my 5-year-old presentation, I was perhaps too enthusiastic about power of actors, and then I said, I think it was not in the slide, but I think I said it verbally, that we don't need any sort of tables, databases aside, like everything which system works with is stored as actor state. Well, it's partially true. Everything which actors themselves work with, yeah, it's stored in event journal. But you don't need to only use actor state, because if you think about CQRS, command query responsibility principle, actors persistence, it's a write part of the system. So it's something which you write into the database during operations. But if you need to generate some reports, for example, you don't need to get it from actors asking state on a cluster level. And this is actually what happened for the first version of the system. We exposed persistent actor state via some web API, And so there was a request coming, what is your state? Okay, I'm running in a cluster. I need to find which shard is running this actor. Okay, then I'm going to ask him, what is your state? He's getting his state. So it took actually some time. Sometimes we saw that this web API was quite slow. And we just need to respect CQRS and build a separate read model. And that really solves all these read questions, read requests, and also it frees our main system from doing its main operational activities. Coming forward, lesson 4. Leave actor state validation to actors themselves. That again brings us to this change of mindset, because in the beginning we were very much sort of monitor dispatcher driven. And this is relatively, actually on a late stage, we still use that approach. We have so-called Mediaset monitor. Why is that? We uploading some files, we're distributing them to the cloud. And then maybe some file is stuck. Maybe some file needs to be re-uploaded and so on. So we have information about current state of TV program. And there is some daemon, which is called Mediaset monitor, which is running continuously. And okay, this guy has missing file quality because we upload multiple files for every TV or radio program. So we need to re-upload that file. And then it calls this actor, okay, please fix yourself. And that was how we did it, because again, we were very much under sort of traditional OP-driven mindset that we need some monitors and dispatchers that take responsibility for things that don't really act by themselves, but actors do. So now we no longer have, actually we still have, but we are on our way to completely get rid of it. We have reminder. Instead of a monitor who's telling, okay, you need to upload some file. We have a reminder, which just sends a message, because actors are reactive. They may fall asleep. And then they will be reminded, okay, do you have something to care about? Oh, I forgot one file. Okay, yes, I'm doing it now. So you only need to periodically push some reactive pieces of code, and then it should be able to look around. Oh, well, I need to take care of myself. This is what we're doing now, and it simplified quite a lot of code and simplified architecture. We have fewer components. And next question or next lesson, which is a derivation of previous lesson. Okay, then we need to schedule periodic reminders actors to themselves. And then when we think about reminders, again, let's think about actors being like physical processes, physical entities. So I'm a human being and I have alarm every day at 6 o'clock usually, because I need to work. Before I need to work, I need to walk the dog. So I get this reminder. So this alarm doesn't tell me what to do, just reminds me, okay, please be awakened and look around. Maybe you need to do something. Oh, I have a dog who hasn't been out for 12 hours. Okay, let's start with it. So if I don't need to go to work, which is Saturday or Sunday, then I don't have alarm. But I can still be alarmed by some external event like telephone, or just wake up naturally, and then I can look around and decide what to do. Have a breakfast, or maybe walk the dog first. So, and this is how well-written actor system actually is supposed to work. So actors are all reactive, and they should sleep most of the time. They shouldn't. They're not running all the time, and they can be part of long-running workflows or ever-running workflow. Because actors, the TV program actually can be updated. It can get new subtitles, new qualities. So there is no end of lifetime of a media set in our product. So it just gets periodic reminders about what needs to be done. And but actors themselves take active responsibility. So all business logic is written in actor's code. It's never reminded about what it needs to do. Just wake up and do something. And there are some standard implementations. You don't need to reinvent the wheel. If you use Akka with .NET, there is Akka persistence reminders, and there is, which we are using. There is Akka Quartz. It's Akka port of Quart library. And lesson 6. It's not really a new lesson, because I was already talking about it in my original presentation 5 years ago. But because at that time it was one of the first lessons which we learned, because already at that time I knew that this is the way to go, or asking actors, not way to go. First of all, ask, because in the actor model, or particularly in its implementation in Akka, both Akka JVM and Akka.NET, you have method tell and you have method ask. So you can actually ask an actor and wait for an answer. First of all, performance of ask is completely horrible, as you can see. So it's just a factor of magnitude, and there is it can be explained. You can find explanation in this article. The reason why it's slow, it really breaks concept of sequential messaging processing, because instead of like getting message sequentially, the actor stops and without accepting more messages and waits for another message, which for response, which must come first, even if though there are some other messages waiting. So there is a lot of bad hacking in ask implementation. But also it completely breaks the actor model as a mirror of real world communication, because when I ask a question, it's not that I'm stalling, I'm just completely paralyzed and not able to do anything before I get an answer. If there is an alarm, that there is a fire alarm, and that we all need to leave buildings, we will all do that without waiting for questions which we just asked. So it's completely unnatural, actually, for actors to work this way. And the horrible performance is just proof from technical side what are the consequences. But you should not be planning your communication in a way that your actors just stop doing anything and waiting for like one single answer. But what if you really need an answer? Then suggestion is to implement a so-called aggregation pattern. So your actor is stateful. It can go from state idle to state awaiting, and then in that state it will still receive messages and it can still respond to them. But if it can't proceed with some main operation while it's aggregating answers to its response, it will still be in this awaiting state, consuming other messages, responding to them. Or if it can't respond, if it needs to wait, it may stash them. It's exactly what if I'm waiting for something and then you approach me, ask a question, and say, "Oh, please wait a little, I need to get an answer." So I can still react on some other events, but I can't answer your question because I'm waiting for something else to clarify. So I sort of stash your message. And then when I get an answer, I unstash your message. Oh, I'm sorry, what was your question? And then I can answer. So this is how good, well-behaving actors should work. So now a few remarks about using actor model or Akka in a cluster. First lesson is actually we followed this. We didn't have to learn the hard way. We followed from the beginning. We did not begin with cluster systems. So if we originally started planning cluster, well, maybe our management would lose the patience because you know, there are some things you really need to get better at when you work when you program cluster systems. So Martin Fowler once said that the first law of distributed object design is don't distribute your objects. Doesn't mean that we can't really use things in cluster. No, of course. What he meant is that you shouldn't really break objects apart. So if you have an actor, you can't take pieces of actor and place them in different part of the system, but as long as what you need to carefully design, how your actors are spread in your cluster, and what happens when cluster nodes lose each other. What happens with if they for a short time stop cooperating? So there are some things to learn, so it definitely adds a new dimension to your system architecture. And while you will need to change parts of your system when you proceed with cluster implementation, major part of your systems or major design it will still be the same. So you can postpone doing these changes until you really need cluster. And so this is you can see that this is our system in a test environment, and there are some nodes running different services, different roles, and you can immediately start thinking, okay, what if all nodes playing some role suddenly gets partitioned, and so they're on their own cluster? What to do? I'm going to say a few words about it, but it just shows that there are some extra complexity added. So lesson 8, applying domain-driven design. So what really helps you to implement, to split actors between nodes in the cluster, so you don't start distributing your object, as Martin Fowler warned. If you spend some time doing sort of domain-driven design and you apply some of its principles, so what typically you need to understand where is your aggregate root. You need to find out your system boundaries and your system split into like entities, values, and then what you do, you build your cluster shards around your entities, around your aggregate roots. So typically, if you have messages coming about different TV programs, so those cryptic names, it's a code of TV programs that we receive in our system. So those are handled by separate actors, and they are spread in different shards across the cluster. So we need to find out the entity ID, which in our case it's this program ID. In bank domain, it can be bank account. So that will be your entity ID, bank account. And then in the cluster, it will be designated shard region, and then so it will be spread around your system that way. And you don't always need to use so-called cluster sharding. If processor is symmetrical, so we have here so-called cluster pool router. It's something, okay, we already identified our cluster shards, and this is a number of files. We just need to upload them to content-driven networks. And then there is a symmetrical set of routers. They don't care about which files they're working with. So the only reason for using cluster here is to balance the load. So here we not use cluster sharding. It's a clustered routers, and Akka uses same strategies for clusters as they use it for non-clustered solutions. You have used smallest mailbox. You can use consistent hashing and so on. Well, we all learned that we should avoid singletons as much as we can, and sometimes we can't. The same goes for clusters. We should avoid cluster singletons because they don't scale. And we had in the first version of the system some singleton, which now we get rid of those which we can. For example, we had a singleton which evaluated system health. And system health is, it looks, okay, is NAS available? Is RabbitMQ functioning properly? Do we have contact with MySQL? Do we have contact with Azure Service Bus? And something is wrong, it gives, okay, it's not healthy. And then we said, okay, there is a lot of checks. Let's have one component that's available for that, and then we only need to do it once in the whole cluster. So it will put it as a cluster singleton. First of all, it's more expensive because now from every node we need to do these clustered calls to find to ask this health check. Second, what if there will be some problem with cluster itself? Then the health check will be just not available, so we won't know what's going on with NAS, what's going on with RabbitMQ, if there is some cluster problem. The cluster problem is not RabbitMQ problem. We'd rather separate them. So there is nothing wrong actually with, even though it comes with some cost, but it's quite cheap just to have health check on every node. So do it symmetrical. So now we have less singleton based approach to that. So whatever we can make symmetrical, let's make it symmetrical. Let's make nodes symmetrical as much as we can. And finally, about clusters is don't rush to heal Splitbrains. So everyone who worked with a cluster solution know that nodes can lose each other. I mean, there can be some network failures, usually short-term failures, sometimes longer failures. And then Splitbrain resolver, basically, it's a decision. Should I kill myself or should I kill everyone else? Because if something is wrong and we don't want two clusters to work simultaneously, think about payment system. Like we have two payment systems, suddenly they form two different clusters and they start paying the same payments twice. So sometimes it's really important to immediately stop it. And then there are some strategies. You have some static quorum. Let's say we have like static quorum, it must be minimum 6. So when something happens, okay, it has 4, let's kill it. But then we have another partition, we kill everyone. So you see, it has some fatal consequences. You have keep majority. You may think it's better, but again, if you continue getting some network failures, maybe some nodes survive which don't have important roles. Keep oldest, keep referee. Oldest is treated separately because the oldest node usually have all singletons, so there are some reasons to keep it. Which means that if there is a partition split here, then it may kill everything else, even though there are some 10 nodes, and just keep the one which has some dedicated node or oldest one. So what else can we do about this? Actually, partitions may just lose each other temporarily, and this is what usually happens. That it just takes maybe a few milliseconds or seconds, and then they find each other. So actually, our code, if possible, should tolerate. Again, if we work with bank applications, we would be more critical to that. But our system is idempotent, so we can tolerate that. So we actually removed Splitbrain resolver strategy from our system, so we'd rather handle it manually if the error persists, than let system automatically decide to kill some of the nodes. So that was 10 perhaps most important lessons that we learned during our life with actors. And I just want to ask you, how many of you tried or actively using some actor model system? Okay, yeah, a few. How many have interest to try it? Yeah, also some hands. Yeah, so then I think we have still about 4 minutes to go, and then if you have any questions, then I can ask them now, and if you don't have questions now, then you can find me on this conference or contact me later. Thank you very much.
Thank you very much, Vagif. And I'm looking at Pine, and there are no questions at the moment. Do we have any more questions? Yes, we have some questions here. Sorry, it's the light, it's hard to see. So, could you say that a lot first here?
Yeah.
And an actor state would be the contents of a file, right?
No, it can be, but for us in our system, the content is more like a black box. It's more like it can be some metadata of the file, it can be some checksum, but not the actual content, but a function of the content. Yeah.
Okay, then maybe my question then does not make a lot of sense, but what I wanted to ask about the right sizing of the aggregate. So let's say you have chess, it's a limited size board, so you can sort of put it all in a single actor and it's fine. But let's say you want to implement infinite chess and your board grows infinitely. How do you deal with that?
Let's keep in mind we have to retell the question to the audience online. And infinite chess. Could you retell the question? Or just retell the answer with the question.
The question was about what if okay, chess has some limited number of cells and moves. When you say infinite chess, you think talking about chess with infinite number of cells? So, well, you will have to, if you want to persist this, you will have to find a way to convert this infinite board into something finite. To give you example of how this, not just related example, for example, there is a Conway's game of life. Which happens on an infinite board, where you start with some initial configuration and then it may grow. Cells may be born, cells may die. So you can still, even though it's infinite board, you can still you can still serialize and persist both moves and configuration, because at any given moment there are finite number of pieces on this board. But if there is infinite chess with infinite number of chess pieces, then I guess there is no way to make it persistent. If number is finite, then I think you would probably persist it. So I don't think it has something to do with actors or like OP or functional programming. You just find some persistence models in order to write it into event journal, because actors write events and they state from events. And if the game is infinite, you can for optimization you can create snapshots. So what Event Journal does, it creates the state of the actor from the latest snapshot. And it's up to you how often you take snapshots. So you can optimize very, very long lifetime of an actor. I'm not sure if it answers the question.
Well, partially, but yeah.
Yeah, it's not an easy question though. So we can continue later maybe to catch up with Vagif. We have one more question. Let's keep it short so we can all finish on time. Yeah?
My question was, you said that you need to persist access, and I assume that you persist them in a relational database. Does any program works with access? Because access, as I understand, are not objects.
We persist actors in Event Journal. An Event Journal may or may not be relational database. We persist them in Event Journal in SQL Server. It can as well be Azure Table Store. It can be Blob. It can be anything. So when persistent actor wakes up, it needs to recover its state, and it just reads series of rows from whatever, either a table store or SQL database. It's a very simple table, so you just need a primary key on ID and some entity ID and sequence number, and you start just reading from 1, 2, 3, 4, 5, blah, blah, blah. Unless you have some snapshots which can make your lives easier, and just you start from snapshot and then read all rows with high sequence number. And what you build up in your actor's memory, it has nothing to do with database. You can build anything. It can be some in-memory state, and it's up to you. So it's not something which you necessarily serialize in the database.
Yeah, so thank you very much for your questions. The time is up, so let's do it in Pine next time. I don't know how long can we cheat the system, so let's write the questions in Pine if you can. But for now, that's it, and let's thank Vagif once again. A round of applause for Vagif.